the Seaboard trucking problem. You're going to find this problem on page 648 to 649 of your textbook. I'm going to read parts of it just so that you'll get the context. And Seaboard Trucking Company has expanded its shipping capacity and purchased 120 trucks and trailers from a competitor. The company located 40 trucks at each of its shipping warehouses in Charlotte, Memphis, and Louisville. So we have our shipping warehouses at Charlotte, Memphis, and Louisville. The company makes shipments from each of these warehouses to terminals in St. Louis, Atlanta, and New York. Each truck is capable of making one shipment per week. The terminal managers have indicated that St. Louis can accommodate 40 trucks, Atlanta can accommodate 60, and then New York can accommodate 50 additional trucks. And then finally, the profit for shipping from Charlotte to St. Louis, Charlotte to Atlanta, and so forth is given in this table. So the question is, how many trucks need to be assigned to each route to maximize the profit? Okay. So we want to formulate this. We've been asked to formulate this as a linear program and to determine the number of trucks that are going to be shipped to each one of these locations. Okay. So again, you should ask yourself the question: what's the decision that needs to be made? And then what are the decision variables? What are the objective functions and constraints? Well, this particular problem is called a transportation problem, and it has a particular structure. And so I want to spend some time showing you a little bit about that structure and showing you how you can use that structure to help you formulate and solve these types of problems that have the structure. And I've got a little graph here, and you'll notice, if you can imagine the outline of the U.S., and I'm going to do a rough drawing. Here's the outline of the U.S. There's the Great Lakes. Here's New England. Here's New York. East Coast. We're coming down to Florida. Come back to Florida around, and then there's the Gulf, and there's Texas, and so these are the warehouses are our red locations, and the terminals are our green locations. And so what we've got is we've got the opportunity from each one of these warehouses. We can ship possibly to each one of these locations. So from Charlotte, we can ship to Atlanta. We can ship from Charlotte to New York. We can ship from Charlotte to St. Louis. And we know also that at Charlotte we have 40 trucks available that we can ship out. Let me choose a different color. That color didn't show up particularly well. We can ship. We have 40 trucks that are available in Charlotte. Okay, well, that's the same situation we have in each one of our warehouse locations. We can ship from Memphis to St. Louis. We can ship from Memphis to Atlanta. We can ship from Memphis to New York. And interestingly, we also have 40 trucks that are available in Memphis to send. And then, of course, we can ship from Louisville to St. Louis, from Louisville to New York, or from Louisville to Atlanta. So those are our, and of course we have 40 trucks available in Louisville. And lastly, we know that in St. Louis, let me go back to the book, St. Louis can receive as many as 40 trucks. Atlanta can receive as many as 60 trucks. And then New York can receive as many as 50 trucks. So that's that captures our problem, except for one thing, because, for example, we know that if we ship, and I'm just going to pick one example, from Charlotte to St. Louis, which is Charlotte to St. Louis is this route. If we ship from Charlotte to St. Louis, we're going to earn $1,800 for each truck that goes on that route. And if we go from Charlotte to Atlanta, we're going to earn $2,100 for every truck that's shipped on that route. If we from Charlotte to New York, we're going to earn $1,600. And that's from the table that we were given, and so forth. All right, so we've got all of the parameters of our problem here. And we've got everything we need to formulate this, believe it or not, as a linear programming problem. So let's move forward and see how we'll do that. The first question is, you need to ask, what are the decision variables? What decisions need to be made? And I wish we had time, had the ability to discuss this a little bit more, but the decision that needs to be made is how many, from each warehouse to let me rephrase this, from any warehouse to, any terminal. That's the decision that needs to be made, is how many trucks. And the objective function is, of course, we want to maximize profit. So those I think are fairly straightforward. I'm going to leave the constraints for a minute, but then the question becomes, how do we translate these into first decision variables, develop a symbol that substitutes for a number, and our objective function. So let's go look at this on the next slide. So here's something I want you to, I've just taken our previous map layout and I've rearranged it into this graph. So what I want you to see is as follows. You'll notice on the left-hand side of this graph, in this area, I've collected all of the warehouses on this side. And on this side of the graph, on the right-hand side, I've collected all of the terminal locations. So this is not a geographic representation, but it represents the warehouses on the left and the terminals on the right. But with respect to each of these are arrows here, still represent the routes available from Charlotte to St. Louis, Charlotte to Atlanta, Charlotte to New York, and so forth. Okay. So now the decision variable becomes, and this is, if we were in class together, we would spend some time talking about this. But what I want you to realize is each one of these arrows throughout this network represents a decision variable. And so as you'll see, hopefully you can count, we have 9 different decision variables because there's 9 arrows. 1, 2, 3, 3 for each, 3 routes for each one of our warehouse locations. And so there's 9 different decision variables. So now the question still remains, how do we define those decision variables? And this is where the creativity comes in. I'm going to designate, and I'm going to designate the letters of the first letter of the variable is going to be the warehouse location. C for Charlotte, M for Memphis, L for Louisville. And the second letter is going to be the location of the terminal. So CS is going to represent the number of trucks travel from Charlotte to St. Louis each week. And so that's going to be one of our 9 decision variables. And so you see we have 9 different decision variables, CS, and they're labeled here on our graph: CS, CA, CN, MS, MA, MN, LS, LA, LN. Those are our 9 different decision variables. We're going to look at a way on the next slide, a shorthand way to define these decision variables. So now for your objective function, how are we going to determine the objective function? So in order to do this, I want to talk about, let's think about this. And let's think about this decision variable CS. In CS, again, CS stands for a number. So if we there's 40 trucks that we send out of Charlotte. If one goes to St. Louis, how much profit is made? Hopefully you say $1,800. If 2 trucks go from Charlotte to St. Louis, how much? Well, it would be 2 times 1,800. If 3 trucks, 3 times 1,800, and so forth. And if you'll notice, I've taken all of the information that was in that table, and the green figures represents the profit on each one of these routes. And so the objective function is going to have 9 terms, and of course we want to maximize our Z value, which in this case happens to be profit. And that's going to be, first of all, 1,800 times our decision variable CS plus 2,100 times our decision variable CA plus so on and so forth, all the way until we get to 2,200. Start with a plus, 2,200 times LN, which is our last, our furthest, our decision variable furthest to the bottom. And this has, the objective function has 9 different terms. Okay, I'll pause for a minute and let you think about that. So each one of these arrows represents a decision variable. Each one of the green numbers is the profit for per truck. And so hopefully you can see throughout this network that you can see the 9 different terms that would appear in the profit function. Okay. If you have questions about this, you should come to the one of the virtual office hours, and I'll try to talk through this again. All right. Now let's talk about constraints. What are the constraints? What are our limits? Well, we're limited by the number of trucks out of each location. So at Charlotte, we can only have 40 trucks that leave Charlotte. Or I can say that alternative, we can have at most 40 trucks to leave Charlotte. We can have at most 40 to leave Memphis, and at most 40 to leave Louisville. Alternatively, at St. Louis, we can have no more trucks than 40 come into St. Louis, no more than 60 come into Atlanta, and no more than 50 come into New York. And so again, what I want to let you see the relationship is how many constraints are there? And if you look, there'd be 1, 2, 3, 4, 5, 6 constraints. There's one constraint for each one of these locations. There's 3 terminals, 3 warehouses, 3 terminals, and so there's 6 constraints. So let's think about how do we deal with these constraints? Well, let's look at this. If for our 40 trucks that are coming out of Charlotte, where can they go? Well, they can only go to St. Louis. They can only go to Atlanta. They can only go to New York. So these 3 paths are the only way trucks can leave Charlotte. And so one of these constraints is going to be of the form, and this is where we need to remember our decision variables. Okay, let me go back and write in our decision variable. For example, I'm going to abbreviate these. CS, CA, CN represent, they are the number trucks sent from location C, Charlotte, to either S, A, or N. Okay, so that's maybe this. Hopefully, this would make a little sense to you. So CSCA is the number of trucks sent from C to either S, A, or N. So our constraint then becomes, what you want to ask yourself, what are the total number of trucks leaving Charlotte? And we know that that has to be less than or equal to 40 trucks. So how do we calculate total number of trucks leaving Charlotte? Well, hopefully at this point you're way ahead of me, and you can see that the total number of trucks leaving Charlotte is the total of CS plus CA plus CN, and that has to be less than or equal to 40 trucks. So that's how we're going to construct each one of these 6 constraints. And at this point, you'll notice that the trucks that are leaving Memphis are MS, MA, and MN. And so similarly, they would have a constraint for Memphis. And similarly, you would then have a constraint for Louisville. LS plus LA plus LN has to be less than or equal to 40. So that's 3 of our constraints. Now we're going to look at the terminal side. We're going to look at the terminal and what's going on at each one of these terminals. And so similarly, you will ask yourself, what's the total number I can abbreviate that. Total number trucks entering, we're going to start with St. Louis. And we know that has to be less than or equal to 40 trucks. So now what you should be able to ask yourself is, well, where do trucks come to St. Louis from? Well, now looking at our diagram, well, they come from these locations, each one of these 3 locations. They come from Charlotte, they come from Memphis, and they come also from Louisville. So there's where those 3 trucks come from. Or the trucks come into St. Louis from 3 locations. And so then in terms of our decision variables, the total number of trucks entering St. Louis is CS plus MS plus LS. Again, this needs to be less than or equal to 40 trucks. And you would do the same for Atlanta, except we're now we have CA going to Atlanta plus MA plus LA is now in this case is less than or equal to 60 trucks. And so the trucks that are coming into Atlanta, again, are coming from either Charlotte, Memphis, or Louisville, and then similarly from New York. Now, one of the things I want you to see is there's a econ term that we can use for these constraints. Maybe you can anticipate what that would be, but the constraints that are associated with in this case, our warehouses are going to be called, supply constraints, because that's where our supply of trucks comes from. And the constraints that are associated with our terminals, you might anticipate that they're going to be called demand constraints. That's where the trucks are needed, they're demanded. And so on the next slide, I'm going to show you the complete formulation and talk about that for just a few seconds. All right. So here's the next situation of the complete formulation, I should say. And I want you to notice this technique where I've used a shorthand. I've used 2 index variables, and an index is an I and J, and that stands, those letters I and J represent each one of our locations. But I and J is the number of trucks assigned to the route from location I, and this on this side is all of our I locations, to J, and on this side, our terminals, are all of our J locations. And again, the objective function, we're going to maximize our profit. You'll see here there's 9 terms. We have our supply constraints here. We have trucks leaving Charlotte, leaving Memphis, leaving Louisville. We have our demand constraints here. These are trucks coming into St. Louis, coming into Atlanta, and coming into New York. And then we don't ever want to forget our non-negativity constraints. All of those have to be greater than or equal to 0. Okay, so this is the complete formulation. I want you to study this and think about this. And as you're doing this, think about this for a few minutes, and then you'll want to follow up and look at the next video where we're talking about the Mystic Coffee problem. The Mystic Coffee problem is going to have a very, very similar structure to this Seaboard trucking problem, this transportation problem, but it has a couple of twists. Okay? Let me know if you have questions.